Hi everyone. This case study will be your guide as we delve into analyzing India's quality data using the exciting world of machine learning. First, download the script and data and save them in the same directory. Then open the Jupyter Notebook script. Before we delve into the data, we need to gather some essential tools. Think of these tools as our virtual lab equipment. Here is what we will using. Pandas SPD. This helps us handle and manipulate data efficiently. Matplotlib as PLT. This allows us to create informative visualizations of the data like charts and graphs. Seaborn as SNS. This builds upon Matplotlib to create even more visually appealing charts. Other helper libraries, you will also use NumPy as NP, scikit-learn, and stats modules for various data processing and analysis tasks. Dataset summary. In this section, we will look at statistical analysis of our dataset. We start by loading the dataset using the pd.read_csv function and specify the encoding. Next, we use the describe method to generate statistical summaries for the four major air pollutants: sulfur dioxide, SO2, nitrogen dioxide, NO2, respirable suspended particulate matter, RSPM, and suspended particulate matter, SPM. These summaries include the count, mean, standard deviation, minimum, first quartile, second quartile, and third quartile, and maximum values for each pollutant. This dataset contains measurements from various Indian states and cities over time, providing valuable insights into the levels of these harmful pollutants in the air. Now let's look at the information in our dataset. We want to know the types of data we have and how many values are missing. We can do this by using the info function. Next, we will describe our dataset to understand the distribution of our data and find out if there are any missing values. We can use the describe function for this. After that, we will check for missing values in each column using the isNull.sum function. It will tell us how many missing values are there in each column. Remember, it is important to handle missing values properly. Finally, we will display the first few rows of our dataset to get a quick look at the data. This will help us understand what our dataset looks like. Dataset info and the result of dataset description and missing values for each column. Remove unnecessary columns from the dataset. In this section, we focus on cleaning the dataset by removing unnecessary columns. We use the drop method to eliminate columns such as STN code, agency, sampling date, and location monitoring station, which are not needed for our analysis. The exists equal 1 parameter specifies that we are dropping columns, and in place equal true ensures that the changes are applied to the original dataset. Next, we use the info method to display information about the dataset, including the data types of each column and the number of non-null values. This helps us understand the structure of our data. Finally, we use the head method to display the first few rows of our dataset, giving us an initial sight of its contents. Missing value analysis. Now we will analyzing missing values in our dataset. We will start by identifying columns with the missing values and quantifying the extent of these missing values. This information will be presented in a table format for easy understanding. The table will have 3 columns: column name, number of missing values, and percentage of missing values. First, we will find the missing value in the dataset using the isNull.sum method. Then we will filter out columns with no missing values and sort by remaining columns by the number of missing values in descending order. Next, we will calculate the percentage of missing values for each column and create a data frame to display the total missing values and percentage. Finally, we will display the missing data summary table. The result shows that the SPM column has the highest number of missing value, followed by RSPM, then SO2, NO2, type, date, and location. Remove outlier. It's important to understand how data is spread out and choose the right way to find the middle value. Outliers, which are data points far from other values, can really change the average, but they don't affect the mode and the median. Since the average is often used, it is a good idea to remove outliers from the important columns in your data to make sure your analysis is accurate. Here's a function that uses the IQR interquartile range method to remove outliers from a column in a data frame. First, it calculates the Q1 and Q3 of the column, then it finds the IQR by subtracting Q1 from Q3. Next, it sets a fence around the data. Any value below Q1 minus 1.5 multiplied by IQR or above Q3 plus 1.5 multiplied by IQR are considered outliers and removed from the data frame. Finally, it returns the data frame with the outliers removed. You can use this function to remove outliers from specific columns in your dataset. For example, SO2, NO2, SPM, and RSPM. Group the dataset by state. In this dataset, we have information about the distribution of major pollutants, including SO2, NO2, RSPM, and SPM across different states in India. Let us start by grouping the data by state and calculating the mean value of these pollutants. We will use the pandas library in Python to achieve this. First, we read our dataset into a data frame. Next, we can display the mean values of these pollutants for each state. This will show us a table with the columns for RSPM, SPM, SO2, and NO2, and rows for each state, along with their respective mean value, and rows for each state. For example, in Andhra Pradesh, the mean RSPM value is 82.55. Mean SPM is 202.77. Mean SO2 is 6.52 and mean NO2 is 25.19. Similarly, other states have their mean pollutant values listed. Input missing values. The dataset has missing values that need filling for further analysis. We will use a method called imputation, which means replacing missing data with estimated values. This is better than just ignoring incomplete data, as it helps avoid issues in our analysis. First, we will group the dataset by state. Then we will define a function input mean to fill missing values with the mean of each group. Finally, we will apply this function to fill missing values in the RSPM, SO2, NO2, and SPM columns using the mean values from their respective states. Derivation for individual pollutant index and AQI. Let's discuss the derivation of the AQI. AQI is a measure used to communicate daily hour quality, indicating the cleanliness or pollutant levels and associated health impact. It focuses on short-term effects of exposure to pollutants. The AQI is calculated on a scale from 0 to 500, with different ranges indicating different levels of health concern. The formula for calculating AQI involves scaling pollutant concentrations to a specified range based on their respective standards. Function to calculate SO2 individual pollutant index SI. Now we are discussing how to calculate the SI for SO2 in air pollution data. The SI helps us understand the concentration of SO2 in the air. The SI is scaled between 0 and 1600. To calculate the SI, we use a formula similar to the one used for calculating the AQI for SO2. We have a function called calculate SI that takes the concentration of SO2 as input. Based on the concentration level, this function calculates the SI. Here is how it works. If the SO2 concentration is less than or equal to 40, we use a simple formula to calculate the SI. If the concentration is between 40 to 80, we use a different formula. Similarly, for concentration between 80 to 380, then 380 and 800, then 800 and 1600, and greater than 1600, we have different formulas to calculate the SI. After defining this function, we apply it to the SO2 column in our dataset to calculate the SI for each SO2 measurement. We then create a new column called SI in our dataset to store these SI values. Function to calculate NO2, individual pollutant index, NI. In this part, we are going to learn about calculating the individual pollutant index, Ni, for nitrogen dioxide, NO2. The Ni value is calculated based on the concentration of NO2 in the air, ranging from 0 to 400. We use a function called calculate Ni to calculate the Ni value. Then we apply this function to our dataset's NO2 column to create a new Ni column. This Ni column represents the individual pollutant index for NO2. Let's apply this function and see the results in our dataset. Function to calculate RSPM, individual pollutant index, RPI. First, we need to understand that the RSPM index category is scaled between 0 to 400. For each RSPM value in the dataset, we calculate its RPI value using the formula By calculating the RPI for each RSPM value in the dataset, we can better understand the impact of RSPM on air quality over time and across different locations. This output of RPI column. In the same way, we have function to calculate SPI using the SPM values. The function calculate SPI takes the SPM value as input and calculates the corresponding SPI. Let's see the first few rows of the SPM and SPI columns to understand how the calculation works. That's the result of calculate SPI. Calculate the air quality index, AQI. To calculate AQI, we need to consider four major pollutants: SO2, NO2, RSPM, and SPM. For each data point, we compare the concentrations of these pollutants and select the highest value to represent the AQI for that point. First, we define a function called calculate AQI that takes the concentrations of the four pollutants as input and returns the AQI. Inside this function, we compare the concentrations of each pollutant and select the highest one as the AQI. Next, we apply this function to each row of our dataset using the apply method. This calculates the AQI for each data point and adds it as a new column in our dataset. Finally, we create a new data frame with the selected columns: state, SI, NI, RPI, SPI, and AQI for further analysis. We then display the first few rows of this new data frame to understand how the AQI is calculated for different states and cities in India. That's the result of AQI column. Exploratory data analysis, EDA. In this section, we will dive into EDA, a method for analyzing datasets to understand their key features. Our goal is to uncover insights using visual techniques without relying heavily on statistical models or hypothesis testing. Now that we have a clean dataset without any missing values, we can start exploring how our dependent and independent variables are related. This will help us understand the dataset better and prepare for applying machine learning algorithms. Let's begin by visualizing our data and looking for patterns and relationships between variables. Through EDA, we can gain valuable insights that will guide us in our machine learning journey. Point plot. We have some steps like fill any missing value in the dataset with the 0. Select only the numeric columns from the dataset. Group the data by state and location and find the average of the numeric columns for each group. This gives the average pollutant levels for each location in each state. Then group the data by state and find the average of the numeric columns for each state. This gives the overall average pollutant levels for each state. Next, create 2 by 2 grid of plots to visualize the pollution levels. Plot 1 shows the average SO2 levels for each state. Plot 2 shows the average NO2. 3 shows the average RSPM. And plot 4 shows the average SPM levels for each state. For each plot, sort the states based on their pollutant levels in descending order. This helps in comparing the pollution levels across different states. Finally, display the plots. For example, SO2, the highest level is located in this state, and this one the lowest level. Heat map. To visualize correlations, you will create a heat map. First, we will select only the numeric columns from our dataset. Then we will calculate the correlation matrix, which shows the correlation coefficient for each pair of variables. Next, we will plot the heat map using the Seaborn library. The heat map will display correlations between variables, with the warmer colors representing stronger correlations and cooler colors indicating weaker ones. And that's the legend of the heat map. For example, we have a strong relationship between RPI and AQI. Rec plot. In this section, we will use a rec plot to visualize the relationship between key independent variables and the dependent variable AQI. This plot shows both the data points and a fitted linear regression model. First, let's check the data types of each column in the dataset. Next, we will filter out the non-numeric columns and create subplots to display the rec plots for each numerical columns against AQI. The rec plot uses Seaborn rec plot function to plot the relationship between each numeric columns and AQI. Let's run the code to generate the plot. That's the result of rec plot. Categorical conversion. There are two main methods, cat coding and one-hot encoding. Cat coding assigns numbers to categories useful for ordinal data. One-hot encoding represents categories as binary vectors. Linear regression. Linear regression is a method used to model the relationship between a dependent variable such as AQI and one or more independent variables such as SO2 and NO2. When there is more than one independent variable, it's called multiple linear regression. To build a reliable model, it is essential to split the data into training and testing sets. We train the model on one set and test it on the other to ensure its effectiveness. The analysis involves calculating metrics such as root mean square error (RMSE), mean squared error (MSE), archaic information criterion (AIC), and Bayesian information criterion (BIC). These metrics help evaluate the model's performance and determine the best fit model. P-values are used in hypothesis testing to determine if the observed data are consistent with the null hypothesis. Data preparation and feature selection. We start by preparing our data. We remove columns that are not numbers and calculate the correlation between the remaining columns. Then, based on this correlation, we select the columns that are most relevant for our analysis. Next, we define our input X and output Y variables. We split the selected columns into two sets and we use a method called backward elimination to further refine our features. Backward elimination helps us remove any columns that don't significantly contribute to predicting the AQI. Finally, we set a significant level and apply the backward elimination process to our data, which is 0.05. This process ensures that our model is based on the most important and relevant features, improving its accuracy. To ensure our dataset is clean, we will first focus on checking for any infinite values in the numeric columns. This step is crucial for accurate analysis. We begin by selecting only the numeric columns from our dataset. Next, we check each of these numeric columns for any infinite values. These values can skew our analysis if not handled properly. Finally, we print the count of infinite values found in each numeric column. This process helps us identify and address any data quality issues, ensuring our analysis is based on reliable information. Building linear regression models. Now you will learn how to build linear regression models and perform cross-validation. This process helps us understand the relationship between variables and predicted outcomes. Linear regression function. To simplify the process, we will create a function for linear regression. This function will help us build models efficiently and maintain code readability. F-false cross-validation. We will utilize F-false cross-validation, a technique that involves splitting the dataset into K-folds. For each fold, the model is training on K1 folds and tested on the remaining fold. This process is repeated for each fold, and average error is calculated as the cross-validation error, which serves as the model's performance metric. Cross-validation. Now we will discuss cross-validation, a crucial step in evaluating the performance of our machine learning models. Cross-validation helps us assess how well our model generalizes to new data. First, we split our dataset into training and test sets using the train test split function. Next, we perform one-hot encoding on the categorical features in our dataset using the getDummies function from pandas library. Then we use linear regression, a simple yet powerful algorithm, to train our model on the training data and make predictions on the test data. After training our model, we perform 10-fold cross-validation using the k-fold and cross-val score. Cross-val score functions from scikit-learn. This technique divides the training data into 10 subsets, trains the models on 9 of them, and evaluates it on the remaining subset. This process is represented 10 times, with each subset serving as the test set once. The average score of these iterations gives us a more reliable estimate of our model's performance than a single train test split. Finally, we print the mean cross-validation score using linear regression. This score gives us an idea of how well our model is performing on average across different subsets of the training data. Linear model 1. In this section, we will explore our first linear model and its summary. Training features SI, NI, RPI, and SPI. Target feature AQI. The analysis of the linear regression model can be summarized as follows. R-squared value of 1 indicates that the model explains 100% of the variance in the target variable AQI. Coefficients. The coefficient for RPI is 0.9966, indicating that RPI has a strong positive coefficient on AQI. All the coefficients are statistically significant with p-value less than 0.05, indicating that these variables are important for predicting AQI in the model. Overall, the model seems to fit the data well, explaining the variation in AQI using the selected features. For model 2, we are using the following features for training: SO2, NO2, and SPM. And our target feature for predicting is AQI. R-squared explains about 11% of the variance in the AQI, which suggests that the chosen features have limited explanatory power for the AQI. and MSE is 101. Linear model 3. For model 3, we are using RSPM, SPM, SPI, and RPI, and our target feature is AQI. The results of third linear model shows a very high R-squared value of 1, indicating that the model explains all the variability of the response data around its mean. This suggests that the model fits the data extremely well, though such a perfect fit could also indicate overfitting, especially with a large number of observations. The coefficient for RPI is 0.99, implying a very strong positive effect on AQI for a 1 unit increase in RPI. However, it's important to note that the p-value for RSPM and SPM are borderline significant, which indicates some uncertainty in the effects of these variables on AQI. Multicollinearity. Multicollinearity is a concept in statistics that occurs when predictor variables in a regression model are highly correlated with each other. This correlation can lead to issues in model fitting and result interpretation because independent variables should ideally be independent from each other. The variance inflation factor, VIF, is a measure that assesses the severity of multicollinearity among factors. A high VIF suggests that the variables have the same variable within the dataset. If the VIF is equal to 1, there is no multicollinearity among factors. However, if the VIF is greater than 1, it indicates that the predictors may be moderately correlated. VIF near or above 5 suggests that highly correlated factors may need to be removed before building the model to avoid high multicollinearity. To calculate the VIF for each feature in dataset, we can use the following Python function. When we calculate the VIF for the first model, we get the following results. The VIF for the SI and RPI indicating a moderate level of multicollinearity, while the VIF for NI and SPI is infinitive, suggesting a high level of multicollinearity. In our second linear model, we have calculated VIF for 3 features, SO2, NO2, and SPM. The VIF value for SO2 is 3.5, which suggests that there is a moderate level of correlation between SO2 and the other variables in the dataset. However, the VIF values for NO2 and SPM are infinitive, which indicates that there is a high level of multicollinearity between these variables and the other predictors in the dataset. Now let's calculate the VIF for the third linear model we have developed. For the feature RSPM, the VIF feature is approximately 60. However, for the features SPM and SPI, the VIF values are shown as infinitive, which stands for infinity. This indicates extremely high multilinearity with other variables in the model. Cross-validate the models. Let's evaluate our models using cross-validation. This technique helps us understand how well our models perform on new data. For linear model 1 with the features Si and Ni, the mean score using linear regression is about 0.1. For the linear model 2, the mean score is around 0.1, similar to the model 1. For linear model 3, the mean score is much higher at about 0.99. However, such a high score might indicate overfitting, so we need to be cautious. In summary, cross-validation gives us insights into our model's performance and helps us choose the best one for our dataset. Stepwise regression. Stepwise regression is a method for choosing which predictive variables to include in a regression model based on their p-values. There are two main approaches: backward stepwise regression and forward stepwise regression. In our example, we use the backward stepwise regression approach to select the features for our linear regression model. We first convert the features to fluid type and then define a function stepwise selection to perform the stepwise selection process. This function iteratively adds and removes features based on their p-value until no further improvement can be made. Finally, we print the resulting features selected by the stepwise regression process, which are SO2, SPM, and NO2. Interaction effect. Interaction effects occur when the impact of one variable on a target depends on the value of another variable. This concept is crucial in regression analysis, where variables can influence outcomes directly or through interactions with other variables. To understand this better, let us evaluate some models. All columns interaction effect. We have calculated the interaction effects for all columns NO2, RSPM, and SPM against AQI. The model is R squared, value is 0.93, indicating a good fit. NO2 interaction effect. Within only NO2, the R squared value is 0.076. Then RSPM interaction effect, considering only RSPM, R squared value is 0.93, showing that RSPM alone is a good predictor of AQI. Regularization. In machine learning, a regularization technique used to prevent overfitting and improve model generalization. We will now apply regularization to our linear models using ridge regression. The code snippet fits a ridge regression model to our data, evaluates its performance, and prints the mean score using cross-validation. Finally, it displays the summary of the OLS regression. The output of the ridge regression model provides several insights into the model's performance and the dataset. R squared of 1 indicates that the model explains all the variability of the response data around its mean, suggesting a perfect fit. However, such a high R squared value could also indicate overfitting. The MSE of 1.83 is a measure of the model's average error. A lower MSE indicates better model performance, but it should be interpreted alongside other metrics to assess model quality comprehensively. Cross-validation mean score. The mean score using cross-validation 0.99 suggests that the model performs extremely well on average across different subsets of the training data. However, as mentioned earlier, such a high score could indicate overfitting, especially if the model does not generalize well to new, unseen data. Overall, while the ridge regression model appears to performing exceptionally well based on these metrics, caution should be exercised due to the possibility of overfitting.